Hello and welcome back to Essentials of Computer Architecture and Organization. We've just completed the major section on processors, and now we're going to be going into the next area where we'll talk about memory. And you might remember me talking about something called the von Neumann architecture. We'll also talk about one other variant of that, which I briefly talked about. So we have the processors, we have the memory, and then we have the input-output. So today we're talking about memory and storage. And so here's a couple of key aspects of memory. There's a couple different technologies that are out there, and it's interesting to be thinking in terms of how they're organized. So first of all, in terms of technology, the technology refers to the type of the underlying hardware. So sometimes at a software or a higher abstraction, you may not think about that, but we're going to get into that a little bit here. The choice determines the cost, the persistence, and the performance. How much it costs, dollars, how long that the data will actually persist in the memory, and what type of performance, how fast it is, and things like that. There's many variants that are out there, and in terms of organization, we want to be thinking about how the underlying hardware is used to build the memory systems. Thinking in terms of the bytes, the words, etc. So those are some organizational decisions. Is it addressable by 8 bits, 16 bits, 32 bits, and so that's an addressable chunk. And what is the direct visibility that the programmer would see, and all that gets into the types of organization. So in terms of the memory characterization, here are 4 main things to consider. Is it volatile or non-volatile? Volatile means that it's not persistent. Non-volatile means that it is persistent, that it will maintain the last memory state that you've put into it. How do you access it? Is it random, that you can go anywhere within the whole memory, or is it sequential? And we'll get into this shortly. It's something called a FIFO, first in, first out. That would be an example of a sequential access. Is it read-write, or is it only read? So can you rewrite the information in that memory, or is it you load it in once and that's fixed, or some subtle variations on that? And how are we going to classify this memory? Is it a primary or a secondary memory? Primary would be, give you an example in terms of computer, you probably heard the term RAM, and we'll talk about that shortly. That would be an example of a primary memory. A secondary memory would be like the hard drive. So first of all, for memory volatility, for volatile memory, the contents that's in the memory disappear when the power is removed. Another factor that comes along this, it has really fast access time, and it's the least expensive. So those are definitely some positive options, at least of the last 2. In terms of non-volatile memory, the characteristic that it has, the contents remain without power. It's more expensive, that's a downside, and it may have slower access time. But quote, if you want to think of this as cheating, but it's just an example of a good engineering decision that may help to get the best of both worlds, is that, for example, in embedded systems, they can have a battery used to maintain the memory contents. And so non-volatile, volatile memory can start to have the characteristics of non-volatile memory. Random access, this is typical for most applications, that you have memory that is used, that is defined in an application or by the operating system, and it keeps conducting where in sort of a random fashion it's going to be storing things as needed, and then when it's done, it'll release that memory and it can be used again. In terms of sequential access, this is known as FIFO, first in, first out. is typically associated with streaming applications, and it requires special purpose hardware to implement that. Well, what are some of the types of permanence of non-volatile memory? The one type is called a read-only memory. Its values can be read but not changed. It's useful for firmware, and you probably have heard of the term firmware if you've worked some with computers. And the purpose is, this is like stuff that you can take to the bank. You can always default. You can put a system reset, a hardware reset, and it'll go back to what is programmed in the ROM. Another variant of this is something called a programmable read-only memory. The contents can be doing, but doing so is time-consuming. The change may involve removing it from the circuit, exposing it to ultraviolet light, and then reprogramming. And so it is effectively, when it's done, it can act like ROM, but if you needed to do some slight updates, you can do that. And you may have had examples with a computer where you get a BIOS update that you're asked to do. In a sense, you have a prom-like function that is going to be updating what you have in your firmware. Another type of non-volatile is flash, and contents can be altered easily. It's used in solid-state disks and digital cameras. If you have a thumb drive, sometimes they're called flash drives, and so that would be another example that you might probably are familiar with. Well, what about this classification between primary and secondary memory? Primary memory, has the highest speed. Takes a lot of power to get that speed. It's the most expensive and therefore tends to be the smallest. Typically, it's a solid state technology. Secondary memory, it tends to be slower speed, it's less expensive, and therefore it's easily to afford to have this be a much larger memory. And a traditional hard drive is where this would be thought of. And so historically, hard drives use some type of magnetic media and electromechanical drive mechanisms to access that. So you have these big disks, circular disks, kind of like if you're familiar with a CD, or even older than that, a record that you might have used for an LP record. So it would be loaded with those, and it would read data from that. What is happening, and it's pretty much almost totally overtaken the market, except for still having very large hard drives, is it's moving to solid state or flash technology. So how does this work in practice? The distinction between primary and secondary, it used to be absolute and clear. Now it is blurring with solid state hard drives that can operate fairly quickly. There is not as much of a distinction. So it's definitely is moving in the direction of a von Neumann architecture, even at a much more fundamental level. The secondary memory is now using solid state technology instead of electromechanical technology, as I just explained. So examples, a flash card is used in smartphones, and maybe you have a smartphone that you can just stick in a flash card and add in more memory, and it can effectively act like more just regular memory. And solid state disks, SSDs, are used in laptop computers extensively now. Gives some really nice boost in performance. If you've had the difference on a hardware, if you on a laptop and you upgraded the hard drive, you probably would notice that significant if you went from a disk hard drive to an SSD. Well, what about memory hierarchy and how that would start to come into play? It's a key concept in memory design. You want to be thinking about the primary secondary trade-off at multiple levels. How much do you want to be investing in primary memory that can take more power? If you're on a laptop, and it takes more power to maintain this, that could drive how much batteries you need. But there's a variety of factors that could come into play, and we already mentioned that SSDs are performing pretty well. So maybe if you're willing to sacrifice a little bit and have an SSD performance to do all of your memory, maybe that might work. Or you get a large enough flash drive of some type where it can do both of these if there's not an extensive, huge amounts of terabytes of information that you need to use. So the basic idea is highest performance memory costs the most. You can obtain better performance, lower cost by using a set of memories, more than one category of memory or something like that. The key is choosing the memory sizes and speeds carefully. Make sure that they're matched with other components. So it's always great to get high performance at low cost. So this would get into the selection of a set of memories based on exactly how much high performance you might need. A small memory has the highest performance using this, the idea we already talked about, the primary versus the secondary memory. A slightly larger amount of memory has sometimes lower performance. And so there are some knees in the curve, if you will, that you need to be thinking about. And some of the material later in the text will talk about that a little bit to give you some ideas of how you could do those calculations. The largest memory has the lowest performance. That's typically your hard drive. And so that's even with the SSD, it's getting closer than what you'd be getting with your RAM in your primary memory. And so what about the types of hierarchical type of approaches that you might be thinking about? You can have dozens of general purpose registers. You can have lots of those, which are very fast, but it's going to take a lot of power. You can have a dozen gigabytes of main memory, and that's becoming very common, getting more and more storage with RAM available in larger and larger packages. And you can have several terabytes of solid state disk. And so you have registers, RAM, and then you have solid state disk. And so how much memory do you have so you don't have to constantly be going back and forth between the hard drive and the main memory? What is a statistically a good number of registers that is going to make it so that you're not going to have to go to memory? So each one of these things, those are trade-offs. So let's do a little bit of a review of the two paradigms for main memory. I've tried to periodically talk about these terms and help you get familiar with them. The one I've talked about most is the von Neumann architecture. And the Harvard architecture, it makes a slight distinction between the von Neumann architecture when it groups all memory together. And so there's an instruction store and there's a data store. So those are different. One memory holds a program and the other holds data. It's used on earlier computers and some embedded systems. And in contrast, the von Neumann architecture, it is a single memory that holds both programs and data, and it is used on most general purpose computers. Thus, the emphasis on general purpose. So what are the consequences of the von Neumann architecture? Instructions and data occupy the same memory. And let's talk about this example. If we just look at a code stub that's written in C, all of these characters, just the way they're written, isn't going to make a whole lot of sense. But if we were starting to think about this, what does this actually specify? Does it specify an instruction or data? There really would be no way to know that unless you had a lot of forensical tools. But Kuber helps us out, and he says on a Spark workstation, it compiles and prints hello world. And so just as a reminder, since this is an older type of platform and you may not be familiar with it, Spark is a computer platform that was made by Sun Microsystems that was purchased by Oracle. And it also talks to the type of processor that it has. It's a MIPS RISC type of processor, a reduced instruction set computing capability. And so that's what it is. So this is the compiled set of instructions that you could load into a Spark workstation. It would understand that this is like just the translation of bits into ASCII characters. And if you were to put that right into the computing capability, it would print hello world. So what are the trade-offs for separate memories? The advantages: it allows separate caches, and we'll get more into this later. It permits memory technology to be optimized for access patterns. So if we're thinking of instructions, you could see how often that's going to be much more sequential. You do one instruction then the other. Sometimes there's branches and stuff like that. So that's the thing that you would need to think about. Data, you definitely would need to have random access. It's based on the input criteria, the interaction with the user or external world parameters that it's made to dialogue with, and then it's going to access the memory accordingly. The disadvantages: you must choose a size for each when the computer is designed, and hopefully that those assumptions are accurate when it's actually used. What about the fetch store paradigm? This is how you would think in terms of the access paradigm that a memory would use. The hardware only supports two options: fetch and store. So the first is a fetch the value from a specific location, and store is to take the information that's in a specific area and load it. You could be thinking of a fetch. You fetch from memory to register, and store, you take memory information from a register and put it into memory, something like that. Programmers often refers to these terms as read and write. And we will discuss the implementation and consequences of fetch and store in some of the later chapters. So in summary, the two key assumptions of memory are technology and organization. We started with that. There's different technologies for how you can save information. And then there's organizational trades that you're going to be making in terms of architecture. Memory can be characterized as volatile or non-volatile, something that it's, as soon as the power is gone, it goes away, or non-volatile, it's going to endure. So RAM would be an example of volatile. ROM would be an example of non-volatile. The types of way that you can access is either random, which is typically more common for what you would do for data, and sequence is more common for what you would be doing for instructions. There can be permanent or non-permanent ways of how you can characterize the memory, and it can be primary or secondary. Primary would be more like your RAM, and secondary would be like hard drive. Separate instructions and data memories has potential advantages, but there is a big disadvantage. And the trend for general purpose computing is to move away from having separate memories and just using the von Neumann architecture, which I described in this chapter. The memory systems use fetch store paradigms, which, as we're talking about here, fetch is, you can be thinking in terms of a read, and store is you're writing things back. So you read things from memory, say load it into a register or a store. You take things from a register and store it into memory. So that's a quick highlight introduction to memory, and thank you very much.